Welcome to the lecture on integer programming. This lecture is for chapter 9 of our course Operations Research. We often face situations where planning models contain integral values of the variables. For example, trucks in a fleet, generators in a warehouse or in a powerhouse, equipments, number of equipments in a factory, and so on. In such a case, we need an integral solution or integer solution. One might think that it is sufficient to obtain the integer solution by using simplex method and then rounding off the fractional values of the variables if there be any. But rounding off may result in suboptimal or infeasible solution. So, in order to overcome these difficulties, a different optimization method which is referred to as integer programming has been developed. In this chapter, we will discuss different solution techniques of integer programming problems, and the whole content of this chapter will be covered in 2 modules. Let us now start our discussion on module 1 of this chapter. Let me first define an integer programming problem first. An integer programming problem or IPP is a type of LPP in which some or all of the variables take integral values only. The problem can be mathematically formulated as optimize, that is maximize or minimize z equal to summation j equal to 1 to n Cj xj subject to the constraint summation j equal to 1 to n subject to the constraint summation j equal to 1 to n aij xj, which is less than equal to or greater than equal to bi I equal to 1 to up to m, and xj is greater than equal to 0 for j equal to 1 to up to n. Here xj's are integral values for j equal to 1 to up to p say, where p is less than equal to n. Now, if p equal to n, that is if all the variables are restricted to take only the integral values, then the problem is called all integer programming problem or all IPP. On the other hand, if some variables are restricted to take only integral values and the remaining are free to take any non-negative values, then it is called a mixed integer programming problem or mixed IPP. When the decision variables are required to take value either 0 or 1, it is called 0-1 programming problem. Let us take an example. Suppose that you have entered in a treasure cave full of 3 types of valuable stones: amethyst A, ruby R, and topaz T. Piece of A, R, and T weighs 3 kg, 2 kg, and 2 kg respectively. And it is also known that the value of amethyst is 4 crores per piece and ruby is 3 crores per piece and topaz is 1 crore per piece. You have got a bag that can carry a maximum of 11 kg. The problem is to decide on how many pieces of each type can be carried within the capacity of the bag, so as to maximize the total value carried. Note that the stones cannot be broken. To formulate this problem as an integer programming problem, we assume x1, x2, x3 as the number of amethysts, rubies and topaz to be carried. Then the problem can be formulated as maximize z equal to 4x1 plus 3x2 plus x3, which is the total value of the stones, and we have one constraint 3x1 plus 2x2 plus 2x3 is less than equal to 11, which is the capacity of the bag. Here x1, x2, x3 is greater than equal to 0 and are integers. To solve this integer programming problem, we can use a very well known method called Gomory's cutting plane method, which I am going to discuss now. Historically, the first method for solving IPP was the cutting plane method, which was developed by Gomory in 1956. In this method, the integer stipulation is first ignored and solve the problem as an ordinary LPP. If the solution satisfies the integral restrictions, then an optimal solution for the original problem is obtained. If not, then an additional constraint is added, and by the name of Gomory, we call this constraint as Gremory Constant, and we add this constraint to the optimum solution. This will effectively cut the solution space towards the required result, and successive applications of these constraints gradually force the non-integer solution towards the desired all integer or mixed integer solution. That is why Gomory's method is called cutting plane method, and obviously the method terminates as soon as we get an integer valued solution. Now, we would like to define how a Gomory's constraint can be constructed. Consider an LPP for which an optimal non-integer basic feasible solution has been obtained as shown in the following simplex table. We have variables x2 and x3 are the basic variables, and the component of B requirement vector are A10 and A20. Since this table shows the non-integer basic feasible solution, obviously A10 or A20 or both are non-integers. For the sake of brevity, let us assume that A10 is fractional. Now, since x2 and x3 are basic variables, therefore, we must have B equal to I2, that is the matrix A12, A13, A22, A23 is equal to 1 0 0 1. From this equality of matrices, we see that A12 equal to 1 and A13 equal to 0. Therefore, the constraint equation A10 is equal to A11 x1 plus A12 x2 plus A13 x3 plus A14 x4 reduces to, if we put the values of A12 and A13, we get A10 equal to A11 x1 plus x2 plus A14 x4. Since A10 is greater than or equal to 0, since it is a component of the recurrent vector B, it must be greater than or equal to 0. So, since A10 is greater than or equal to 0, the fractional part of A10 must also be non-negative. Now, we split off each of A1j in equation 1 into an integral part I1j and a non-integral or non-negative fractional part F1j. Then equation 1 may be written as I10 plus F10 is equal to I11 plus F11 whole into x1 plus x2 plus I14 plus F14 whole into x4, and this gives F10 minus F11 into x1 minus F14 x4 is equal to x2 minus I10 plus I11 x1 plus I14 x4. Therefore, if we add an additional constraint in such a way that the left hand side of equation 2 is an integer, then actually we are forcing the non-integer A10 towards an integer. Thus, the Gomory's constant is F10 minus F11 x1 minus F14 x4 is less than or equal to 0. To verify the truth, if possible, let us assume that F10 minus F11 x1 minus F14 x4 equal to h, where h is greater than 0 and integer. Then we have F10 is equal to h plus F11 x1 plus F14 x4, which is greater than 1, and it contradicts the fact that F1j is a fraction. Thus, we have the fractional card F10 minus F11 x1 minus F14 x4 is less than or equal to 0, and this gives minus F11 x1 minus F14 x4 is less than or equal to minus F10, and this gives minus F11 x1 minus F14 x4 plus G1 is equal to minus F10, where G1 is called a slack variable, and by the name of Gomory we call it as Gomory's slack variable. Thus, an additional constraint is to be included in the given LPP in order to move further towards obtaining an optimal integer solution. After inclusion of this constraint, the optimal simplex table looks like as shown in this slide. You see that one additional row, that is the third row, is included, and as well as one additional column for G1, the last column, is also included. And from the values of the component of B, we see that minus F10, which is a negative quantity, and because of this negative quantity, we cannot proceed further by using simplex or by using the regular simplex method. So, in order to resolve this problem, we will proceed by using dual simplex method. And as you know, in dual simplex method, we have the optimal criteria, we are satisfying the optimal criteria, but we are getting infeasible solution. So, we will proceed to get an feasible solution. So, after getting this solution, the above procedure is applied for construction of second fractional card if needed, and the process is to be continued as long as we are not getting all integer solution. Now, I would like to explain the cutting plane algorithm. To find the computational result, we have to follow some steps. In step 1, we use simplex method to find an optimal solution of the problem, ignoring the integer restriction. In the next step, that is in step 2, we examine the optimal solution and terminate the iterations if all the basic variables have integer values. Otherwise, we proceed to the next step. Step 3, we construct a Gomory's fractional card from the row, say the kth row, which contains the largest fractional part, say fk0 of the basic variables, and we add it to the original set of constraints. The Gomory's constraint can be obtained as minus summation fkj xj, which is less than equal to minus fk0, and by adding Gomorian slack variable, we can make it as an equation minus summation fkj xj plus g1 is equal to minus fk0, where 0 is less than fk0 less than 1 is a fraction, and 0 is less than equal to fkj less than 1, fkj can take the value 0 also, it is also a fraction, and G1 is the Gomorian slack variable. In case of a tie in the largest fractional part, we can choose any one arbitrarily. In the next step, we add the cutting plane generated in step 3 at the bottom of the optimum simplex table obtained previously. Then we proceed with the dual simplex method to find the optimum solution. If the solution thus obtained is integral valued, then this is the required optimal solution of the original IPP. Otherwise, we return to step 3. So far, we have discussed the basic concept of integer programming, and we have discussed the Gomory's method for solving all integer programming problem. We will now take some example to show how Gomory's algorithm can be applied to find the solution of all integer programming problem. Consider the following IPP: maximize z is equal to x1 plus x2 subject to 3x1 plus 2x2 is less than or equal to 5, x2 is less than or equal to 2, x1, x2 is greater than or equal to 0 and are integers. So, this problem is an all integer programming problem. First, we ignore the integer restrictions and solve the problem by usual simplex method. For this, the given problem can be written in standard form as maximize z equal to x1 plus x2 plus 0 into x3 plus 0 into x4 subject to 3x1 plus 2x2 plus x3 equal to 5, x2 plus x4 is equal to 2, x1, x2, x3, x4 is greater than or equal to 0. Here x3 and x4 are the slack variables. The following table gives the optimal solution in simplex. In the first iteration, we see that from the zj minus cj values, z1 minus c1 as well as z2 minus c2 are negative and both are equal. So, arbitrarily we choose z1 minus c1 and obviously a1 will be the entering vector, and from the minimum ratio we see that a3 will be the departing vector. In the second iteration, we have a1, a4 in the basis and zj minus cj values, so that the optimality condition is not satisfied because z2 minus c2 is still negative. So, a2 will be the entering vector in the next basis, and from the minimum ratio we find a4 is the departing vector. In the last iteration, zj minus cj is greater than or equal to 0 for all j. Therefore, the optimality condition has been satisfied, and this gives the optimal value x1 equal to 1/3 and x2 equal to 2. Since x1 is not integer, we have to proceed further by using Gomory's cutting plane method. Since the optimal solution is not integer, we consider only the fractional part of x1 equal to 1/3. So, we can write it as 0 plus 1/3, and in the first row we have also a14 equal to minus 2/3, and it is a negative fractional. Therefore, we write it as the positive fractional part. So, a14 equal to minus 2/3 can be written as minus 1 plus 1/3. Let G1 be the first Gomorian slack, then we have the Gomorian constraint minus summation f1j xj plus g1 equal to minus f10, and this gives minus 1/3 x3 minus 1/3 x4 plus g1 equal to minus 1/3. So, using this Gomorian constraint, the optimal simplex table looks like this. We have an additional row, that is the third row, and additional column, that is the last column, and since the component, third component of the recurrent vector B is negative, so we cannot proceed with the usual simplex, we have to follow the dual simplex method. And the method, dual simplex method, tells that we have to choose the first departing vector. So, obviously, G1 will be the departing vector, because there is only one negative component, and then from the third row we see that we have two negative components, minus 1/3 and minus 1/3, and their corresponding Zj minus Cj values are 1/3 and 1/3. Therefore, we compute Zj minus Cj by this negative component, and we find the maximum of 1. Since both the ratios are -1 and -1, therefore, we choose arbitrarily A3 as the entering vector. Now, we proceed as usual, and finally, we see that the components of the vector B are all positive. This means that the feasibility condition is satisfied, and hence the optimal integer solution is x1 equal to 0 and x2 equal to 2, and the corresponding max value is equal to 2. Now, we proceed to take another example. Maximize z equal to x1 plus 4x2 subject to 2x1 plus 4x2 is less than equal to 7, 5x1 plus 3x2 is less than equal to 15, and x1, x2 is greater than equal to 0 and are integers. Now, the problem can be written in standard form for simplex as maximize z equal to x1 plus 4x2 plus 0x3 plus 0x4 subject to 2x1 plus 4x2 plus x3 equal to 7, 5x1 plus 3x2 plus x4 equal to 15, and x1, x2, x3, x4 all are greater than equal to 0. Now, if we put this problem in the simplex table, we see that in the first iteration the optimality condition is not satisfied, whereas in the second iteration the optimality condition is satisfied as Zj minus Cj is greater than equal to 0 for all j. And from the second iteration of this table, we see the result as x2 equal to 7 by 4 and x1 equal to 0. Since the optimal solution is not integer, that is x2 is not integer, we consider only the fractional part of x2 equal to 7 by 4, which can be written as 1 plus 3 by 4, which is equal to 1 plus f1. And similarly, 39 by 4 can be written as 9 plus 3 by 4, which is equal to 9 plus f2. Since maximum of f1, f2 is equal to maximum of 3 by 4 and 3 by 4, which is equal to 3 by 4. Therefore, we can select any one of these two arbitrarily. We choose f2 equal to f2 0 equal to 3 by 4. In the second row of the last iteration, we have a2 3 equal to minus 3 by 4. Therefore, we write a2 3 as minus 1 plus 1 by 4. Let G1 be the first Gomorian slack. Therefore, we can write the Gomorian constraint as minus f21 x1 plus f22 x2 plus f23 x3 plus f24 x4 plus G1 equal to minus f20, and this gives minus half x1 minus 1 by 4 x 3 plus g 1 equal to minus 3 by 4. Now, we place this Gomorian constraint in the optimal simplex table and we use dual simplex method. This slide shows that the component of B, the third component of B is negative. So, the departing vector will be obviously G 1 and then from the maximum ratio we find the entering vector as A 1 and then proceeding ultimately we see that all the components of B are now non-negative in this table and therefore, the feasibility condition in dual simplex method is satisfied, but the optimal solution is still not integral because it gives x 1 equal to 3 by 2 whereas x 2 equal to 1. From the last two rows of the last iteration, since maximum of f 2 f 3 is equal to maximum of half and half which is equal to half, we arbitrarily choose f 2 equal to f 2 0 equal to half. Also, we write a 2 3 equal to minus 5 by 2 which is equal to minus 3 plus half. Let G 2 be the second Gomorian slack, then we find the Gomorian constraint as minus half x 3 plus G 2 is equal to minus half. We now place this second Gomory constraint in the optimal simplex table and again we use the dual simplex method. Now, this slide shows that the feasibility condition is not satisfied because the components of B are all non-negative. Therefore, we choose G 2 as the departing vector and A 3 as the entering vector and we proceed for the next iteration. This slide shows the final iteration. So, feasibility condition is satisfied here as well as we find the integer solution x 1 equal to 1 and x 2 equal to 1 and the corresponding maximum value z equal to 5. In this module, we have introduced integer programming and we have mentioned that there are two types of integer programming problems, all integer programming problems and mixed integer programming problems. In this module, we discussed the Gomory's cutting plane method for all integer programming problem and we have also demonstrated the method taking some examples. With these comments, we end this module.